recording and hand it off to the first tutor.
Hi everyone, my name is Sam and I'll be covering the first topic for today's concept review. Let me share my screen. All right, can everyone see my screen? All right, perfect. So I'll be covering fall 2019 midterm 1, question 3. It's definitely on the harder side of the questions. There's a lot of conceptual background you need to know. And it covers Ramachandran's diagram, protein structure, DNA supercoiling, and let's get started. Oh, for some reason I can't. Oh, there we go. Okay, so part A. Part A says that there's a 10 residue peptide consisting of only hydrophobic residues that spans the lipid bilayer, and it asks which of the following 3 Ramachandran diagrams describes the conformation of this peptide. And as you can, just to go over what the Ramachandran diagram is, it defines a set of dihedral angles that a given peptide backbone can have. And what these dihedral angles are the angles between the alpha carbon and the adjacent nitrogen and the carbon in the carboxyl group. And they're defined by psi and phi respectively. So since each of these amino acids have a unique R group, only a set of these psi and phi angles are allowed to avoid a steric clash between these R groups. And as you can see from the picture in the bottom left-hand corner of the slide, only a given set of these psi and phi angles are allowed. And with these given, with these allowed angles, you get the beta sheets, the alpha helices, and the left-hand helix structures they've all learned so far. So it's a good thing to memorize this plot because you'll know as a general rule where you'll find the beta sheets and the alpha helices. So let's move on to the part 1 and 2 of this question. So now that we know where the alpha helices and the beta sheets are in this Ramachandran diagram, the question essentially boils down to, is this peptide only a beta sheet? Is this peptide an alpha helix? Or is this peptide consisting of both alpha helices and beta sheets? And to answer this question, the question provides you with 2 hints. Feel free to unmute or just type in the chat. What do you think these 2 hints are in the question? They'll help you decide between these 3 different structures. One of them, yep, exactly. It consists of only hydrophobic residues. And I think the other one is pretty obvious. It's in bold. It only consists of 10 residues. So now that we know that it's only 10 residues and it only has hydrophobic residues, we can try out and see which one makes more sense. So let's say if it was an alpha helix, we know that alpha helices have a 1.5 angstrom rise per turn. So in total, if it was an alpha helix only, it would be 15 angstroms long. But we also know that membranes are actually 30 angstroms long. So if it were only an alpha helix, it would not be enough. So we can cross off C as an option, leaving B and A as the 2 other choices we have. Since there's hydrophobic residues and the lipid bilayer is also hydrophobic, the protein has to form a very specific structure. So it allows these hydrophobic residues to interact with the lipid bilayer while also kind of hiding away the polar amino acids. And the only way you can do this is to form a regular secondary structure, so a beta sheet or an alpha helix. And that's why we can conclude the answer has to be a beta sheet, because as you can see in the structure, a beta sheet allows the protein in a way to make sure that the polar groups are towards the inside or towards the above or under the membrane, and the nonpolar groups can interact with the lipid bilayer, as you can see here. And moving on, this question had a third part. This one asks, does the peptide enter the membrane as a monomer or just a single unit or a multimer? In the chat is, so this would be a beta barrel. Yeah, that's actually the answer to this question. These beta sheets, in order for them to actually span across the membrane, they can't just be a single monomer, because not only is that not long enough, but also if it were only a monomer, it can't hide away those hydrogen bonding groups from hydrogen bonding groups of polar amino acids from those non-polar tails. So that's why for it to actually be stable in this non-polar environment, it has to form these beta barrels, as Matthias says in chat. This way, it can kind of, I guess, the beta barrel structure, and this, as you can see in this picture, it's in a way that there's no uncompensated hydrogen bonds. So for it to be stable, it has to form this beta barrel structure. And just as an aside, that's why also alpha helices are very stable in the plasma membrane, because they can form in a way so the nonpolar groups are facing towards the outside to the tails, and the polar groups are facing towards the inside. So that's why it'll be stabilized. Are the hydrogen bonds, you refer to the hydrogen bonds between the peptide backbone? I'm referring to the hydrogen bonds that the polar groups in the amino acid form with the outside, so with the solvent. In this case, the outside is going to be the non-polar lipid tails. So that's why the answer would be a beta barrel. And it'll have to be a multimer, not a monomer. Are there any questions? All right. So on the so on the outside, so it's going to be mostly nonpolar groups, but there's always going to be somewhat polar, some polar groups. So that's why whenever there's a beta sheet in a plasma membrane, you can assume it'll form a beta barrel. That's the most stable conformation they'll adopt in the plasma membrane.
Could I ask another question? Sorry for asking so much.
Yeah, go ahead.
But so it's kind of related to one, I guess, because it's like these two, I thought that the reason we did the beta sheet was because of the hydrophobic residues. But instead, is it because of the length of an alpha helix? Is that why we choose the beta sheet for part?
Yeah, that's why we can cross off alpha helix. Alpha helix is the answer, because it says that it's only 10 residues long, and since it's going to be, and for alpha helices, this has a 1.5 angstrom rise per turn. So that's why we can just cross off alpha helix as an answer. And I think in lecture it was covered that there's only two types of membranes that can cross the that was covered in lecture. One were the alpha helices, and the other was the beta barrels. So that's why you can deduce that it's a beta barrel. Does that make sense?
Yeah, it does. Thank you. It's just like all those little things that had to come together.
Yeah, it's definitely a conceptual heavy question. All right, with that, I think we can move on to the next part, part B. This question focuses on supercoiling. And just as a primer of the basic concepts you know to answer this question, DNA replication introduces supercoiling by adding new base pairs. And when you overwind DNA, when you're adding when you're twisting DNA in a right-handed sense, you're overwinding it. But when you're unwinding DNA, it's going to be twisting in a left-hand sense. And the parameters, if you know, for supercoiling are twist, T, is the number of DNA turns with reference to the local axis, the keyword being local, right? W is the number of crossings, so the number of times DNA comes over itself. And then finally, the linking number L is the number of turns globally. Again, the keyword being global. And then the right of a DNA compensates for the twist. To understand what that means is that, let's say in this example, you have 1,000 turns. You do one left-handed turn, so now you have 999 turns. But now that both ends of the DNA are fixed, the DNA is in a high energy unstable conformation, and so for it to go low in energy, the twists it as kind of a zoom in of the picture. It no longer twists, but to keep L the same, W becomes -1. So overall, the L remains the same. And so negative supercoiling is a natural consequence of DNA replication. Why is that? Well, if you look at the picture in the question, DNA is fixed at both ends. So since L is a number of global turns, L must remain fixed. And initially there's no twists, but when you're adding nucleotides, DNA goes in that high energy conformation. So to go back down to a stable conformation, T must increase. But since L is constant, thus, based on this equation, L equals T plus W, W decreases. I was initially going to ask you guys to answer these questions, but since we're low on time, I'm just going to answer myself, and then you guys can work on yourselves afterward. So the question initially asks, what is the twist before adding base pairs? So in the question it says there are 5,000 base pairs, and there's going to be 10 base pairs per turn. So 5,000 divided by 10, the initial twist will be 500. But then you add 50 base pairs, so you do 550 divided by 10. Now you have a 505 twist. And then the change in linking number, again, since both ends are fixed, the linking number does not change, so L remains the same. And then finally, the right, L equals T plus W. Initially, W is 0, so T equals L. So initially, L is 500, and then T becomes 505, and so that's why W must be -5. And just as a gut check, this makes sense since I said that replication induces negative supercoiling, and that's why W must be negative in this case. So that makes sense. And then finally, the last part says that why is this happening? What's the conceptual reasoning behind this twisting and supercoiling? Well, as you guys have known before, that a major source of stabilization in DNA is base stacking, and base stacking is optimal when there's a 36 degrees per turn. So that's why when you add the twists, the DNA goes away from this optimal base stacking. And so to go back to that optimal base stacking for the most stable structure, the restoring force is from the electrostatic complementarity between the partial charges of the bases. So that's why there's a restoring force back to that 36 degrees. And then part C, this is, I think, the easiest question out of the three. The concept being tested in this case focuses on ion channels. You guys talked about it when talking about bacteriorhodopsin. So it's asking proton conducting channels usually have acidic side chains, but what happens if you change these side chains? Will it still work? So as I said before, in the transmembrane proteins, most amino acids are nonpolar, but the polar ones have a very specific function. And in this case, the aspartic and glutamic acids have a specific function in that they conduct protons across the channel and donate H+. But if you were to change, and then it's asking, can asparagine and glutamine do this? But if you change them, these two aren't charged, so they can't do the same accepting and transferring protons. So the answer would be no, the channel would not work. And then finally, it asks for the importance of water. And as you can see in this picture, water kind of acts like a bridge between these polar amino acids, in this case, aspartic acid, and it continuously passes down the protons until the protons are transferred from one side to the other. So yeah, and that's the function of water and these proton channels. Yep, that was the question 3.
Hello, everyone. Right, give me a second. All right. I am Lisa, and today I'll give you a quick walkthrough of how to tackle a blossom problem. I will be talking about midterm 2019 question 4. So I know you've been going through a lot of review of blossom matrix yesterday, and so before we go into the equation, one thing that hugely helped me understand what's going on in blossom matrix is this graph. So knowing that these alignment blocks are not a couple of random amino acid sequence being placed randomly next to each other, but actually they are alignment of regions of known protein families that share a common ancestor. But we want to know how similar they are to nowadays. So that's what's. So the core of Blossom score is really the substitution likelihood Lij, and which is given by the ratio of 2 probabilities. On the top, it is the probabilities of observing Ij substitution in the alignment block given to you in the problem, and on the bottom is the random probability of observing Aij substitution in the same alignment block, but with all amino acids all scrambled randomly. So how do we do that mathematically? I think you all know the equations. So for the P actual, it is the number of observed Ij substitution in the block divided by the number of all possible amino acid substitution in the block. And for the P random, it's actually accounts for the amino acid abundance in the alignment block. So I usually interpret it as the frequency of I and J. So mathematically, it is 2 times the frequency of I times the frequency of J in the alignment block. So you can take a closer look at that. Some other things to notice is L and S are interchangeable, and S is based on the logarithm, and L is really a likelihood. So each L and S refers to the substitution of one amino acid pair. So if they were asking you to calculate the relatedness of 2 sequences, you can, using the probability rule or sum rule, to basically add up all the S or multiply or times all the L for each substitution to give you this S sequence or L sequence A and B. S sequence A and B, yeah. We'll go through that problem later together. And also notice L is a more direct representation or a more direct quantitative interpretation. A substitution score, L equals to X means it is X times more likely to observe the substitution than by random chance. So if they were asked you to figure out the relative likelihood, like, so you can approach that from L instead of from S. We'll go through that example later. All right, so now let's do the problem together. I'll give you a second to look at this problem. All right, so the first problem is asking for how many CG substitution are there in the sequence blocks. So we do that by looking at the columns. So you look at each column, right? And in these columns, there's only C or there's only G, meaning there's no substitution happening there. Only in one column, there's one C and one G, and they can form a pair. So that means there's only one substitution going on in the whole sequence block, in the whole block. So question 2 is asking for how many possible substitutions of any amino acid in this sequence block. So still we're looking at columns. There are 10 positions in each of the columns. Each position can be substituted by 9 of the other. And there are 10 columns in total. And because the orders doesn't matter, we need to times 0.5 divided by 2. So that gives you the answer. All right, so number 3, what is the probability of finding CG substitution in the sequence block? So this is asking for P actual. Actually, I think you should really just memorize this, what this P actual is, by just memorizing this statement. The probability of finding CG substitution in a sequence block, that means P actual, which means the observed frequency. So that is really just the ratio of problem 1 and problem 2 that we just walked through. Is there any questions so far? All right. Okay, so number 4, the probability of finding CG substitution by random chance. Understanding this is account for abundance. So using this equation, 2 times the frequency of C times the frequency of G, and basically you just count all amino acid, the number of all amino acid, which is 100, the number of all C, which is 4, and number of all G, which is 2. And then we plug in the equation. All right, so this is asking you relate PCG actual, PCG random, and SCG. Notice this is Blossom score, which is just two times of the log of base of 2 to the likelihood. And likelihood is given by the ratio of 2 probabilities. So I think you definitely can figure that out by yourself. All right, so let's look at part B. Part B is asking for the relative relatedness of 2 pairs of sequence A and B, and sequence A and C. So you're comparing the relatedness of sequence AB to the relatedness of sequence AC. So based on what we just talked about, you can use this sum rule to add up all the Blossom score to figure out the total Blossom score for a sequence. So you can So you can do that by so for the Blossom score of sequence AC, you just add up 4 losing substitutions, losing self-substitution score. And for sequence AC, you can add up 4 substitution score for each of the substitution. But notice I really want to talk about is that you can use a trick and just account for the difference in the substitution, ignoring all the similar substitution. How do you understand that? It's a simple math derivation. So because they're asking you the relative relatedness. So as we talk about, we approach from L, and we substitute L by S, which is given to us in the problem. And then S is basically a sum of all substitution, right? And then we just plug in all the sum, and then the similar term will cancel out, leaving us only the difference. So the trick, so based on the trick, we can just write down the answer for the question simply by calculating because this Is there any questions so far? All right, so let's look at part C, which is different. So the first part is asking you to recognizing A, B, and C form DNA. I have my method doing this, you have yours, doesn't matter. So I would like to, first of all, I would like to look at Hennis, and that gives me either C form or AB form. And I would like to differentiate AB form based on the orientation of each base pair, seeing if they are parallel to each other or they are more disordered. I think approaching to a groove is also okay, but for me, it's kind of hard to tell because in either case, you have this alternating wide and narrow, and sometimes it's just hard to tell. But from the orientation of base pair, see in diagram A, they are more ordered in terms like of they're all parallel to each other, and B, they're like tilted against or twist against each other. So we can say that diagram A, because it's right, so diagram 3, obviously it's a C form because it's left-handed, and diagram A, it's B form, and diagram 2, it's A form. All right, so next is asking you the difference of major groove and minor groove. Notice major groove is used for sequence specific recognition in B form because it will give you 4 distinct hydrogen bonding patterns in major groove, whereas in minor groove you only have 2. But also notice the dimension is also important because in A form, the major group is too narrow to accommodate common protein structure. All right, so what forms can be adopted by RNA? Notice one major difference between RNA and DNA is this 2' hydroxyl group. In DNA, which is characterized in B form DNA, which is characterized by this C2 endo conformation, the 2' hydrogen will be in close contact with 3' phosphate group. But if you replace the 2' hydrogen with a hydroxyl group, which is the case in RNA, that 2' hydroxyl group will generate steric clash with 3' phosphate group, so that RNA cannot adopt B form. It will adopt A form. And the last point is just knowing that repeated CG pairs is favored by C form. I want to ask you if RNA can adopt C form. How do people think? What do people think? Can RNA adopt C form? Why is that? Yeah, why is that? You can just unmute yourself. It's a very quick answer.
Oh, it's because it has an additional OH group. And if it adopts C form, there'd be some sort of like repulsion.
Right. You are right. Because C form is given by this alternating C2 endo and C3 endo. So you also have this steric clash between C2 hydroxyl group and C3 phosphate group if it's in RNA. All right, so that's all I have today. Put your question in the chat box and we'll take a look. Thank you.
Okay, hi everyone. So today I'm going to talk a little bit about thermodynamics, heat expansion, and how it relates to work. And so I think this kind of marks a transition in the course where for the next 1/3, you'll be talking a little bit more about thermodynamics towards getting a better understanding of entropy and ultimately connecting this to chemical equilibrium, which will be very useful going forward in the course. So with that being said, kind of the starting point of our discussion is just the first two laws of thermodynamics. And the second law is something that I think will be discussed much more in depth later. Just for now, you can refer to it as the law that states that for a given reaction, entropy can never decrease. The change in entropy for both the universe and the system combined can be 0, but it can't decrease. But what's going to be the focus really more of the presentation today is the law of energy conservation, which says that if you take a given reaction or any type of process, whenever we're dealing with thermodynamics, we can kind of draw arbitrary boundaries between what is a system and what is the surroundings. So based on the way that we define those two things, if we look at the total energy of both, it should be some constant. And also this means that when you're looking at the energy change of the system, it should be a direct negative of what happens to the surroundings. And so with that in mind, we can go to the example that's been used pretty frequently throughout the class, which is this gas expanding inside of a piston. And so in this case, we can define the system as just the gas itself, and we can define the surroundings as everything that is not the piston. And in this case, we make a few simplifying assumptions. So namely that the gas that we're dealing with is a monoatomic gas. And the main reason for that is because if we want to model the internal energy as only consisting of kinetic energy, meaning that the only energy that the molecules have is that they bounce around and that there's no rotation or anything else going on, that's the main reason why we say that it's a monatomic gas. It just simplifies some of the equations. And so with this idea of making a boundary between what is the system and what is the surroundings, what you can use to think about an example like this is to think about this in terms of inputs and outputs. So if you want to calculate the change in energy of the system, you could consider what happens at the input level and what happens at the output level. And so for this context, really the main input is typically just going to be that heat is added into the system. There are also cases in which work is done to the gas, meaning that the cylinder is compressed. And then in terms of outputs, the most common output would be that the gas expands and does work, thereby losing energy. And in some cases, there can also be heat loss. And so this is a pretty important equation in terms of understanding this. So if you want to see how the energy of the system changes, you look at what happens to the heat flow and what happens to the work. And as a note on sign convention, I think the best way to remember it is anything that increases the energy of the system will be positive. So in this case, if heat flows into the cylinder, that's positive heat flow. And anything that decreases the energy of the system should be negative. So if the gas expands and does work, it's using its own energy to do work. And by energy conservation, that means it's losing its own internal energy to add energy to the surroundings. So in that case, the work would be negative. So this is just kind of an important equation to understand the relationship between those concepts. And also, this is another useful equation that's very important for homework and as well as midterms, which is that the internal energy of an ideal gas can be modeled by this. And this is because we're only considering kinetic energy, so this is for an ideal monoatomic gas. Any questions so far? Okay, I'll keep going. And so the next thing that I just briefly want to point out is how we kind of look at gas expansion as a type of work. So if you recall from physics, the definition of work is just force times the distance that is applied to the force. Force does not always have to be constant. It can be some function. But basically, it's kind of given by this. And in our specific scenario, you can look at the expansion as like delta S, or change in distance. But if you also recall that force is pressure divided by area, and that the distance is essentially volume divided by area, you can kind of rearrange this equation and you get that work is equal to the pressure that you're doing the work against, as well as the change in volume corresponding to that increment. And so this is again from your textbook. You can see that the total work that's done by the gas would be the external pressure times the change in volume, because the gas is pushing against whatever pressure is on the outside. And just another note on this is that the amount of work that's done by a gas can also be quantified by just looking at a pressure volume graph. Because if we said that work is pressure times the volume, notice that if you take the integral of this curve, basically meaning if you just find the area in this region, it's pressure times volume. So the units will work out, meaning that this is work. And this becomes relevant for understanding the two different types of gas expansion, which I'm going to just briefly cover now. So the first is reversible expansion. It's also thought of as near equilibrium expansion. And so to understand what's happening in this example, just one observation that is always helpful to keep in mind is that wherever the level of this piston is, just keep in mind that that level is pretty much determined by two different pressures. There's the internal pressure of the gas, and there's the external pressure that's from the surroundings. And the level of that piston is always going to be determined based on the difference in pressures. And it's only if the pressures are equal that the piston stays in place. But as soon as the internal pressure is more than the external pressure, then you have a slight increase in the movement. And so what happens here is, if you want to imagine what's going on in a reversible process, you can essentially think of it as really slow expansion, where the external pressure is like very, very slowly decreased. And one really great way to think about this is that if you think of all the pressure on the outside as being composed of just having a ton of marbles on top of this piston, and you just take off one marble at a time. And so you're very slowly decreasing the external pressure, which is allowing the system to do a little bit of work. So it just moves slightly every single time. And if you want to think about how you could calculate the work for this process, you could essentially say, well, if we remove the first marble, there will be a very small change in volume at the original system pressure. And then for the next iteration, we'll remove another marble. And so now the system pressure will decrease again a little bit more with the same incremental change in volume. And this will kind of go on and on. And you can kind of look at this graphically, and over a very long period of time, this is what it looks like. And so essentially the process that I described of taking a very small difference in pressure and then multiplying by the change in volume can almost be thought of as a Riemann sum. And then if that triggers any memories from calculus, then that's because it can also be quantified in terms of taking the integral of this expression here. And so again, what helps us is that because we're using an ideal gas at a constant temperature, you can substitute the system pressure for the ideal gas law, which is, if you recall, PV equals nRT. And then since we're integrating with respect to volume, you'll arrive at this expression. And so the kind of output or result of this equation is really useful for problem sets and also midterms going forward. Any questions so far? Okay. And so to continue, I have a quick question for everyone, but I think we're running a little bit low on time, so I'll just explain this. So now this is the other type of pressure expansion, which is constant pressure expansion. So in the previous example, what was happening is that the pressure was decreasing a little bit every time, and we were doing a little bit of volume expansion. But another type of expansion is if you just took all the marbles away at once and you dramatically decrease the external pressure, then the work that you'd be doing is kind of just given by a flat line, because you immediately drop the external pressure to a given point, and then you allow the cylinder to expand. And so because the work can be calculated by just computing the area, if you looked at the PV graph for that type of movement, you would essentially get that this is the initial pressure times the change in volume, which is PI times VF minus VI, also written as dV. And just really briefly, I want to just talk about the definition of enthalpy. This is something that will be discussed in much more detail later on. But enthalpy is defined as the internal energy of the system plus pressure times volume. And the key thing is that this is used to measure heat flow, but at a constant system pressure. And this is important for a lot of biological situations because there can typically be a very constant system pressure. Or also you can use enthalpy to describe any process that occurs in a near equilibrium fashion in which the system pressure kind of stays the same. So the previous graph that we showed would not be a direct application of when you could use enthalpy because the system pressure slowly decreases over time. But in a case where you have isobaric expansion, meaning that you heat a cylinder in a way that the pressure stays the same, but it slowly expands, that would be a case in which you can use enthalpy. But this is going to be discussed in more detail later. And yeah, just it's useful to link internal energy and heat flow for biochemical reactions, which you'll see in later portions of the course. So that's all I have. Up next, you're going to do some midterm practice on applying some of these formulas, but does anyone have any questions? Okay.
All right, hey everyone. So I'll be building on what Poojan just talked about by going over question 1 on fall 2019 midterm 2. We're a little short for time, so I'll go kind of quickly, but just so you know, I put some notes through my slides on how I approach these problems. So if you go through these slides again later, just look out for those. So let me get my pointer and let's get into it. So here's the question stem. So you have a system with 1 mole of an ideal gas at 300 Kelvin. It's an isolated system. Pressure is initially maintained at 2 atmospheres by a piston that's fixed, is then released, so you have constant external pressure. It expands against a constant external pressure of 1 atmosphere, and you increase the volume by 1%. And they gave us this conversion of 1 atmosphere is equal to 10 to the 5th Pascal. So part 1 is what is the initial volume of the system? And it says express your answers in units of meters cubed. So well, we have the quantities moles, temperature, pressure, volume, and it says an ideal gas, so we should think, all right, let's use the ideal gas equation, rearrange it so we can solve for what we want, and just plug in the quantities given to us. We have 1 mole. It's at 300 Kelvin, so RT, the quantity R times T, is approximately equal to 2.5 kilojoules per mole. You can also just plug in the gas constant, 8.314 multiplied by 300 Kelvin, but this is just faster, and pressure of 2 atmospheres. And we'll end up getting 1.25 kilojoules per atmosphere. Now from here, let's convert. And we're given something in conversion with atmospheres, so that'll be useful. Let's look at what a Pascal is. And this is where it's useful to either have your conversions and SI units memorized or written down on a cheat sheet. 1 Pascal is 1 joule per meters cubed. We want meters cubed, and our joules will cancel out. So from here, it's just simple dimensional analysis to cancel out units. And we'll end up with 0.0125 meters cubed as an initial volume. So we'll come back to this term, so keep that in mind. Next question is, what is the value of work being done by the system during expansion and expressed in terms of kilojoules? So important thing to note here is that we're doing expansion against constant external pressure, meaning we can use this simple equation, which I will explain again a little later when we go to part 5, but we can take -1 times the constant external pressure, which is 1 atmosphere or 10 to the 5th meters cubed, times our change in volume, which is simply from part 1, the initial volume times 1%, 0.01, get -12.5 joules or -0.0125 kilojoules. And we can do a quick check. We have a negative work, meaning that work was being done by the system on the surroundings. And that makes sense because we're expanding, the gas is pushing outwards. So that all makes sense. Cool. Part 3 is, where does the energy to power this work come from? So here are 2 important questions to ask yourself. First, what type of system are you looking at? In this case, it's an isolated system, meaning no heat is being exchanged to or from the surroundings. And second question is, what is actually in the system? And here, as given in the question stem, it's an ideal gas. So how do we use those to answer this question? So because it's an isolated system, there's no energy that's going to be coming in or out of the system that'll be affecting this expansion. And as Poojan talked about with the total energy, you have dq, which is your energy transfer term, plus work. But because it's isolated, your dq term is equal to 0. So all the energy of the system, any changes, is just going to be attributed to work, and therefore what's inside of the system. And what is inside the system? An ideal gas. And go back through your definition of what an ideal gas is, and you know that there will be no potential energy interactions. That's important. So when we answer this question, we can be as specific as possible and say, this expansion energy must come from the kinetic energy of this ideal gas, just pushing against the container walls, and that's forcing the expansion. So that's how we break down part 3. Part 4, what is the final temperature of the system? So we want to first ask ourselves, what is temperature related to? What equations or quantities can we use to solve for temperature? In this case, we can use kinetic energy to do that. And the second question would be, how is kinetic energy going to relate to work in our expansion? So here's the kinetic energy equation that we just went over, 3/2 nRT. And we can actually solve for the initial kinetic energy first by just plugging in what values are given to us. We find initial kinetic energy is 3.75 kilojoules. Cool. Now we can look at how does work affect this initial kinetic energy. And overall, if you usually would have some sort of conservation of energy, right? Except unless there's some external work being applied in this case. So what this means is we can take our initial kinetic energy and add whatever work's being done, in this case, negative 0.0125 kilojoules, and we can end up with our final kinetic energy after our expansion. That's 3.7375 kilojoules. So that's just a conservation of energy equation there that we utilized. And now we can plug back into this equation by rearranging the solve for temperature. And our final temperature, using this term, is 299.7 degrees Kelvin. And again, we can double check that because we had expansion and work being done. The gas has pushed against the containers of the wall and probably lost some energy because of that. So overall, we have lower kinetic energy and therefore lower temperature. All right. So final question is, the expansion process is being done in a different way. The external pressure is going to be reduced from 2 atmospheres to 1 atmosphere like before, except we're going to do it in a series of small steps. Will the final system temperature be lower or higher than in the previous case? Previous case being what's given in the question stem here. And they say do it qualitatively, don't do any calculations. So what we want to do here is first just compare the two processes. What's different? And we just went over this graph, but let's talk about this. So let's take the first process. So it says pressure is initially maintained at 2 atmospheres by a piston that's fixed in place. So the inside of this piston has a pressure of 2 atmospheres. And if it's fixed in place, that means the external pressure has to also be 2 atmospheres, right? You have equal pressure coming from both sides, inside and outside, so nothing moves. So external pressure is 2 atmospheres, which we'll say is right here. We'll pretend that's 2 atmospheres for now. And then it says piston is released, so gas expands against a constant external pressure of 1 atmosphere. So if it's constant external atmosphere, what that means in this terms of this graph is we're starting at 2 atmospheres, and then we get this instantaneous drop in pressure down to 1 atmosphere. And then at this 1 atmosphere pressure, we have our expansion, volume expansion. So there's first the initial drop in pressure and then expansion. And as Poojan talked about, the area under the curve here, our external pressure times the change in volume, is the amount of work being done in the system. So all the work for the first process is just whatever's under this red arrow. Now let's look at what the question gave us for part 5 is, okay, let's say we decrease the pressure in small steps as shown here. So we do the same thing. We have this small instantaneous drop in pressure and then expansion happening, except we're doing that in smaller steps and much slower. So we have a small drop in pressure, then expansion, small drop, expansion, et cetera, et cetera. And as you can see, if you look at the area under this curve now, it's a lot bigger compared to just this instantaneous drop in pressure from 2 to 1. So that's the idea between expansion against constant external pressure versus expansion against a reversible or near equilibrium expansion. you're doing more work. More work is going to be done by the system on the surroundings in a near equilibrium expansion. What does that mean in terms of temperature? Let's go back to our conservation of energy equation. So if more work's being done, that work value is going to be more negative compared to what we calculated in part 2. So if this term's more negative, our final kinetic energy is going to be lower. And as we saw before in the previous part, lower kinetic energy means a lower final temperature. So that's the main idea here, is comparing the differences between a constant external pressure expansion versus reversible expansion. But yeah, that is all I have for this question. Does anyone have any questions? All right, well, I will post these slides right after this, so thanks.
Okay, so that's the end of the concept review. So thank you everyone for coming. I think we'll take about a 5-minute break and then we'll get started with the homework session. So yeah, we'll see you all at around 6:06.